3.3 vectors in planes. First, depending on at what point in your life you took geometry, you were introduced to vectors, or you might not have been. But more than likely, you have been introduced to vectors at some point in your time. Why do we use vectors? We use vectors because of the fact that we have magnitude and direction when we talk about things like velocity or force, for example. Magnitude and direction. So first, when I talk about vectors, we have an initial point, that's the starting point that we're starting at, and then the terminal point is kind of like at a point in time. This would be like a ray. So the vector looks very similar to a ray, where you have your starting point and a point in time. Now you have a magnitude, which would be the angle in which you are moving, and you have your direction. Sorry, direction is the angle in which you're moving, and magnitude is the actual pace that you are moving. Okay? So a lot of times if we're finding magnitude, we use our distance formula, or we're talking about kind of like a squared, b squared, c squared, but we will get into that. So when we're talking about vector v in a plane, we use lowercase letters to represent the plane, but we can also use points like this to represent our vectors. So for this first example, it's saying, show that these two are equivalent. Well, these two vectors, this is vector v, this is vector u. If we want to show that they're equivalent, we can use that distance formula. So the distance formula is, again, that distance formula is always very similar to the Pythagorean theorem. The difference is that we have two coordinates instead of one. So if we look at RS first, we get the square root of 13. Now, a lot of times people will ask the question, wait, you put 1 first and it says x2. You can label x1 and x2 however you want, but we take our difference of our x's, subtract our difference of our y's. We square those and we add them together. Notice why I leave it as a square root. So when we're comparing, we should leave it as square root. I want you to pause the video and find the distance of PQ, vector PQ. And we get the square root of 13. Now this next part is talking about component form of a vector. So you can read through this, but really what a component form of the vector is saying, like the length in x compared to the length in y. So my component form here, right here, I take this subtraction and I would get -3. When we typically write component form, though, we want to be positive. So let's say we take 4 subtract 1, we would get 3. And if we did 4 subtract 2, we get 2. This is component form. So this is another way to see if these two are equivalent. If our component forms are equivalent, then that means our actual distance, our vectors will be equivalent. So 3 take away 0 is 3, and 2 take away 0 is 2. Again, you can do this either way when you're doing this x2 minus x1. So these are my component forms for RS and PQ. So if you look at example 2 right here, it's saying find the component form for these 2 points, my initial point and my terminal point. So when you do this, you want to take your terminal point, subtract the initial. So same type of thing, why I rewrote it up there. So my terminal point is this. So I'm looking at my vector. I would take my -1, subtract 4. -1, subtract 4. And then here I'm going to take my 5, because that's my terminal point, subtract -7. 5, subtract -7. So my vector component would be a -5 and a positive 12. -5, positive 12. So again, this is my component form. Now I'm also asking for magnitude. So since I already have this magnitude, this is where we can take the square root of my vector or my component form, and we have -5 squared plus 12 squared, and the square root of that would be the square root of 169, which would be equal to 13. So here's my component form, and here is my magnitude. Now we have vector operations. So let's say we have these two vectors, vector u and vector v. Now if you look, this vector u did not change in this gray. So what I could do is shift this up and over so that my terminal point on u is the same point as my initial point for v. And now when I add these two vectors together, I would get a new vector. So when I add two vectors together, it's just adding the x's plus the y's. That will give us a new vector that's formed. When we are doing vector operations, we are just focusing on the x's kind of values with the y values. In this case, though, we're taking our whole v, so this is saying 2 times my vector -2, 5, and we multiply both of them by that. So my new component would be -4, 10. Again, it's just algebra to both components. If I'm going to do W subtract V, so my W, my X value for W, so it'd be 3 minus -2, and I have my V value, so W minus V, and now I have my second value, W minus V. So I get 5 because this becomes a plus plus, and -1. Pause the video and try to do this one. So now we have a unit vector. Our unit vector is the direction of V. So when we're finding a unit vector, a lot of times we have this U equals our unit vector. We have our V divided by the magnitude of V. That's going to be our unit vector, which can also be written as 1 over the magnitude of V times V. These are the same thing. So the magnitude of V is what we have been doing with our x squared plus our y squared, our magnitude with the square root. So an example for our vector is already in component. Okay, so this is our x and our y. So that's how far over you are and how far up you are when we're talking about this vector. So when I'm writing this out, it's sometimes more easier to see in this component. Our magnitude is 1 over the square root of our x vectored squared, so -2 squared plus our 5 squared. That is our magnitude, this part right here, times our actual vector, so -2, 5. When I actually multiply this out, writing it in vector format, we would get -2 over the square root of 29 and 5 over the square root of 29. Because again, when we're multiplying our operations, we take the 1 over the square root of 29 and multiply it by both. Now we want to verify that the result of the magnitude is 1. So same type of thing that we just did here. We would take the square root of -2 over the square root of 29 squared plus 5 over the square root of 29 squared, and we could get the square root of 1, which is 1. So we do verify that the result of this magnitude is 1. Okay, now let's look at this next question. We want to actually find the vector. We already know the magnitude is 5 in the same direction as this vector, which is -2, 3. Again, it can be a different place, but it's in the same direction as vector V. So our first step is we want to find the unit vector. So our unit vector of V, which if we look at this, -2, 3, we can have our vector -2, 3, and on bottom, our magnitude of this would be the square root of -2 squared plus 3 squared. So our unit vector is right here. But now we want to find the vector that correlates with W, or vector W. So in this case, since we know that W will be equal to 5 times our unit vector, so here, right here is our unit vector, would be the 3 over the square root of 13. Now, because of our vector operations, we can multiply that in, and our vector W will be equal to a -10 over square root 13 and 15 over square root 13. Now when we're writing a linear combination of vectors, so initial point here, terminal point here. When we're talking about our combination or our vector components, we use it in the form of ij. So a lot of times when we think of our linear lines, we have x, y. Well, when we're talking about vectors, to keep the two separated, we talk about ij instead of x, y. But there's the same kind of idea that you have in your brain already. So if I find my vector component in between my initial point and my terminal point, I get this as -3, 8. Now again, when we're talking about vectors, if we want to write this in the standard format of ij, I is like our x format. That's going to be a horizontal when I'm moving horizontally, and vertically is our j component. So when we write this, we can have -3i. I write it as a cursive so I don't forget that I have a point with it, plus j. So this right here in unit vectors, a -3i plus 8j. One of the reasons we want to have vectors written in standard unit vectors is because we can do any algebra to these vectors in standard unit. So it's saying u is equal to this, v is equal to this. Find this new vector operations. Now that it's written in this format, it's much easier to do this algebra. So I want you to pause the video and try to attempt to do this, knowing these two vector components right here by yourself. And you should have gotten negative 12i plus 19j. Because again, this is stuff that we have learned starting back in actually 5th grade, 4th. I don't know. You guys are just smart people. So now I get into directions of angles. So if we have some vector u that looks like this is the same thing as saying the cosine of theta and sine of theta, because we're looking for this direction, this angle theta. Now, this would also be true when I'm looking at my ij, like we just said. Now, when we're talking about direction, we also have to indicate our magnitude. So our magnitude here would be our written in this format. Now, it's always going to be much easier to rewrite something so that we can understand it with as less algebra at the beginning if possible. So we have a quotient rule. We have a rule that tangent of theta is equal to sine theta over cosine theta. So let's say we use this information right here, looking at our vectors. Let's say if we multiplied by 1, if we multiply both the top by 1 and the bottom by 1, we would get this equation. If you look back at this right here, when we're trying to find the magnitude, this number right here, right in front of the j, that could be, let's call this a b. B, because this is the exact same thing in our vector component, linear vector could be our b. And if you look right here, this is like our a value. So when we're talking about our direction, as long as we have it written in our linear vector model, then we can take the number right in front of our j, which is kind of like our y, divided by our a, and have the tangent of that angle. So when I'm looking at this right here, I can say my b is 3, and my a is also 3. So this right here is my ratio of my angle. So this is saying tan of my angle is 3 over 3, using what we already have. So tan of my angle is equal to 1. If you wanted to draw a picture roughly of where this is, remember I is kind of like my x, so I would be over 3 up 3. So if I drew this right here, this would be 3 over 3. I'm in my first quadrant. So again, that's the 1. And if I have my opposite and my adjacent, 1 over 1 would be my 45-degree angle. So let's say if I have something like this. So first, if I try to draw a little sketch of where this is at, this is over 3, and this is down 4. So it would be in the 4th quadrant, over 3, down 4. So tangent of my angle right here. So I have tangent of my angle is equal to my opposite over my adjacent, using this right here, what we have previously learned. Now we don't have a special right triangle for this. This is where we're going to have to use our graphing calculator. If you do arctan of negative 4 over 3, that will be equal to negative 53.13. When we're talking about angles, though, I don't want it in a negative angle. So I'm going to do 360, because that's this angle here is that negative 53. I'm going to do 360 minus this 53.13. So this angle is going to be equal to 306.87 degrees. That's my direction of this vector. Vectors are all great, but why do we have them? Well, let's get into some applications. Again, these are just the tip of the iceberg of what we can do with vectors and what people do with vectors. So a couple things, it says there were 20 below the horizon. Notice that meaning that this whole angle is 200. So 20 plus the 180 that we have right here. And it's saying that we have a speed or a magnitude of 150 miles per hour. Now, when we're talking about this, we're using this magnitude as just per hour. So obviously this plane is going to keep on keeping on. That's asking for what the vector component would just be within 1 hour. So I'm looking at this, we can use this equation. Our magnitude times cosine theta will be like our x component, and our magnitude times sine of theta is like our y component. So if I plug in the things I know, again, this right here is my magnitude, that's like my length, and we get this. Now we can simplify this right here in our calculator, knowing that this is in degrees, not radians. So what we would get is, so now my actual vector component then, when I'm writing it as a vector, is negative 140.96, comma, negative 51.30. You can always check this. If I take this number squared plus this number squared, and then take the square root of that, will that be equal to 150? I don't know. Pause and check if you want. So on this next one, when I'm finding weights, we're using vector to determine weight. So again, vectors can be used for many different types of units. Now, before we can actually start answering the question, we have to kind of understand what this is doing here. So when we have something like this, we always first have something that's pulling down on us. We have a vector that's pulling down on us. This is what we call gravity. We're doing straight down a perpendicular line from the earth. So gravity is forcing that trailer and that boat. Okay, that's what AD is, or DA, sorry. BA is our force of gravity. Now this right here, BC, notice how it's a little bit turned, but now this is using right here the weight of the boat. BC is going to be the force against the ramp. So this is forcing down on the ramp. So this length right here, this AC, that's that 600 force that is needed to push it up the ramp. That 600 is with our AC. Now, if I took this triangle right here with our actual force of gravity, our restrictions on the ramp, and if I turned it, that'd be like the same triangle that's right here. So this 15 degrees is kind of like this 15 degrees, but it's just written in a different format. So what are we actually looking for again? It says our combined weight of the boat and the trailer. So again, that's what gravity is. So that's this part right here. If we're looking at this triangle or this triangle, we can say that sine of 15 will be equal to, in this case, my opposite. So that's the magnitude of our pulling. So that's our AC divided by the magnitude. This is what we're looking for, or magnitude of our AB. So what do we have that we can fill in here? Well, our AC value is that 600 that's pulling. Remember, that's the part that's pulling it up. So I can replace the magnitude AC with sine of 15 is equal to 600 over the magnitude of AB. So how actual heavy this boat is. I can multiply this over and divide this over. So now what I'm actually looking at is this equation. Again, this right here is our combined weight of the boat and the trailer. So I do 600 divided by sine of 15 into my calculator. I would get that the boat and the trailer would be roughly about 2,318 pounds. Wowzers. You're like, well, yeah, I have something to do that. Someone had to know how to figure out vectors before you can use anything on your phone or anywhere else. So the reason we can be living the life we live today is because someone before us came this far. So that's all I have for you folks. Have a great, have a grand, have a wonderful day.